Hello. In this presentation, we're going to look at the section in Chapter 10 that deals with probability. And this is another one of those topics that you could certainly take an entire class just on this topic of probability. But we're going to look at some of the basics, so just what probability really sort of means and how we calculate probability, how we assign probabilities to things, but just sort of at a basic level, just so we get a sense of how it works. So here's some of the kinds of things that we might wonder. What are the probability of these things happening? So the simplest possible one that I can think of really is what's the probability of a coin flip landing up heads? That one's pretty obvious, and we'll certainly deal with that one since it's such a simple example. I'll use that a lot in the coming presentation. These other ones are more complicated. How likely is it to rain tomorrow? Well, you have to use a lot of background information, knowledge of weather patterns and which sorts of weather patterns are likely to generate rain, which one aren't. Here's another one, right? What's the probability of a specific result from a specific sporting event? Again, similar to predicting the weather, you use sort of background knowledge and your expertise, how much do you know about the teams and the game and so on. And here's a particularly difficult one that scientists spent decades trying to gather the information necessary for getting a good sense of what's the probability that humans are to blame for climate change. And with these three ones, there's a lot of kind of uncertainty involved there, and a lot of good scientific work can reduce that uncertainty quite a lot. So predicting what the weather is going to be like just one day in advance, that's actually gotten pretty good. And depending on what the teams are and what the game is, you can oftentimes have a pretty good sense of who's likely to win. And scientists with all these decades of work set this probability very high, that humans are very likely to be responsible for at least a big chunk of climate change. But what we're going to deal with in this presentation are these ones that are more straightforward assessment of probability, things like coin flips and rolling dice and drawing cards from a deck of playing cards. These are things that we know so much more about these situations that we can have very high confidence for assigning probabilities to these things. And so in addition to just assigning basic probabilities, we're going to look at sort of calculating probabilities here and calculating probabilities of sort of combined events happening together and things like that. All right. So, as usual, a little bit of stage setting here to start off with. So, a tautology, remember, is a statement that's guaranteed to be true. That is, it's impossible for it to be false. Well, if it's impossible to be false, then the probability of it being true is 1, right? 100%. It's guaranteed to be true. On the other hand, for a contradiction is impossible to be true. So what's the probability that it's true? 0, right? 0% chance of it being true. Everything else that's not a guaranteed truth or a guaranteed falsehood lies somewhere between 0 and 1 for its probability. All right, so a few more concepts here. They're going to be very important as we move through this. The idea of mutually exclusive statements or mutually exclusive events. These are things that cannot both be true at the same time. Or if we're talking about events, it's 2 events that cannot happen at the same time, or 2 different outcomes that can't both happen at the same time. And the coin flip is, as is often the case, the most straightforward example of this. It's just not possible when you flip a coin for both heads and tails to land face up. It's got to be just one or the other. So those are mutually exclusive outcomes of a coin flip. Same thing with rolling a die. If it's just a regular 6-sided die, there's nothing special about it. One of the sides is going to be the one that lands up, right? One of the numbered sides will land face up. You can't have more than one face of the die land face up. And so the 6 different sides, right, those are the mutually exclusive options for what will result from rolling one of these die. Another concept, a jointly exhaustive list of possibilities. So this is the set of statements or the set of events that exhaust the list, right? This gives you all the possibilities that could result from this. So again, coins and dice. So coin flip, heads and tails, those two options, jointly exhaustive. Those are the only two things that can happen under normal circumstances, so, setting aside like something weird where it lands in some little slot and so it like lands on its edge or something. But if it's just on a flat surface, a coin flip really only has these two options, heads or tails. So that's the jointly exhaustive list of possibilities. For the die roll, pretty similar, just there's more possibilities. There's 6 sides to a standard die. So when you roll that, there's 6 different things, right? It could land 1, it could land 2, or 3, or 4, or 5, or 6. And that list is the jointly exhaustive list of possible results from rolling a simple die like that. Okay, so now getting on to actually assigning probabilities to things and starting with, as usual, the easiest example. So here's the symbols that we use for this kind of a thing. Capital P for probability, and then the thing that we're trying to figure the probability of is in the parentheses right after the P. So this is the probability of X, or if we want to spell it out even further, the probability that X is true, or the probability that X will occur. And so for a coin flip, super easy. What's the probability that the coin will land heads? 0.5. Right, 50% chance, 1/2 chance, however you want to express it. Those are sort of equivalent ways of expressing it. The standard way is the number between 0 and 1. So that's largely what I'll stick with, unless the decimal gets to be this sort of weird complicated number, as we'll see with cards when we've got 52 different options. 52 different options in the jointly exhaustive list. Spelling out sort of the decimal places there, it looks a little messy. So when we get there, we'll switch to fractions, as we'll see. Another thing to notice here is this very important principle, the principle of indifference. So for a coin flip, as long as you don't have reasons to think that this is a rigged coin, that it's not the case that both sides are heads or both sides are tails, or that it's somehow set up so that it's more likely to land on one side than the other. So most coins are like this, right? They're just sort of standard. You don't have any reason to believe that one side is more likely than the other. So for all of the items on the jointly exhaustive list of possibilities, you give them all the same probability. And since we only have 2 options here, we give them both 0.5. They both have a 50% chance of happening. Here, notice that if we add together the probabilities in the jointly exhaustive list of possibilities, it should add to 1, right? So what's the chances that the coin will land either heads or tails? Well, those are the only 2 possibilities, right? That's the jointly exhaustive list. So one of those has to happen. It's got to be one or the other of those. So the chances of one of those happening is 100%. 50% for heads, 50% for tails. Add them together, you get 100%. This is, as I'll mention this in more detail later, but this actually is what's called the restricted disjunction rule. It's a the restricted disjunction, because we're asking what's the chances, what's the probability of either heads or tails. Remember, the or is a disjunction, and so when you have an or like this, when that's what's being asked, is what's the probability of this or that. The shorthand way of remembering what to do is when you see an or, you add the probabilities. And so that's what we've done here, and we get 100%. And we get 1.0. For the dice, so I don't have the jointly exhaustive list of possibilities here. I just have 2 out of the 6. So what's the probability that the die, when I roll it, will land with the 2 face up? Well, that's 1 out of 6, right? A 1/6 chance of it landing like that. For the 5, same thing, right? This is 1 out of the 6 faces of the die. So if I were to roll it, there's a 1/6 chance that it will land 5. And so then what if I want to ask, so what's the probability of it landing either 2 or 5? Well, it's an or, And the restricted disjunction rule tells me that when I see an or like that, then I add the probabilities together. So that's what I do down here. 1/6 plus 1/6 is 2/6, which reduces, simplifies down to 1/3. So 1/3 chance of either 2 or 5. All right, moving on. So another important concept that we'll have to keep track of is this idea of independent statements or independent events. This is when the probability of one has no influence on the probability of the other, right? These things are just happening independently. They're not interacting with each other, causing sort of probabilities to change back and forth somehow. And so here's a simple example. Let's say that I've got in one hand a coin, in the other hand a 6-sided die, and I throw them both onto the table. And I can ask them, what's the probability of the coin landing heads? And the probability, I could ask, what's the probability of the die landing on 5? This is just the same as thinking about the probability of these things completely separate, right? Because these are independent things. Even if I'm sort of throwing them onto the table at the same time, still the event of the coin landing one face up or the other side up and the die rolling, these are independent from each other. So this is the way we look at them, right? So now we can think of this. What's the chances of them both happening, right? So what's the chances when I throw the coin and the die onto the table, what's the chances of this result, of the coin landing heads up and the die landing 5? So intuitively, the chances of both of these things happen, the probability of both of these things happening should be less than the probability of either one of them happening alone. Think of it this way. So what's your betting confidence? Like if you were to bet $1 on the results here, and you were betting $1 on just the coin landing heads. Like, okay, well, that's 50-50 chance, right? So it's not fantastic odds, but it's not totally horrible odds. But now, what are the chances of the coin landing heads and the die landing on 5 at the same time? Well, that decreases the probability, right? So, even if the coin lands heads, it could be that the die lands on 4 or 3 or 2 or 1 or 6, right? So there's all these other options that could make you a loser still, even when the coin landed heads. So the probability of both of these things happening should be less than the probability of just the coin flip on its own, or just the die landing on 5 on its own. All right, so that brings us to the restricted conjunction rule. Remember, and is the conjunction. And so that's why they call it the conjunction rule, and it's restricted because it's restricted just to independent statements or events like this. So really easy to calculate this. When you get a conjunction, an and, then what you do is you multiply the probabilities together. And so that's just what we've got down here. The probability of heads times the probability of the die landing 5, well, that's 1/2 times 1/6, and that gives you 1/12, which is a substantially smaller probability than either one of these other things alone. So that matches sort of our intuitive guess as to what's going to happen. Okay, now let's go back to disjunction, right, where we've got the or. What are the chances of at least one of these happening? Well, that should be higher than either one alone. And same thing, to get an intuitive sense of this, we do the same thing we did last time. What's your betting confidence of just the coin landing heads? Well, that's 50-50, right? It's 50% chance. Now, let's say that you'll be a winner if the coin lands heads or if the die lands on 5, or both. So, like if you see the coin land and it lands tails, well, you're not a loser yet. There's still the possibility that the die lands on 5. That'll still make you a winner. So the probability of you winning is higher in this combined case than either case alone, right? And so for a disjunction like this, we add the probabilities together. And this brings us to the restricted disjunction rule, which I already alluded to before. But it's disjunction because we've got an or, and it's restricted because it's just applying to independent statements or events, like a coin and a die landing, sort of on their own. So simple calculation here, right? The probability of the coin landing heads plus Remember, this is plus because we've got an or. It's the disjunction rule. So the probability of the coin landing heads plus the probability of the die landing 5, 1/2 plus 1/6 gives us 4/6, which just reduces down to 2/3. So pretty good chance now, right? I'd bet on that maybe, depending on how much I was asking to bet. Certainly better than just betting on a coin flip. Okay, so back to conjunction and independent events, right? So we've got the restricted conjunction rule applying again here. Well, now let's say instead of having the coin and the die being thrown onto the table at the same time, let's say that I take just the coin and I flip it once, see the result, and then I flip it again and see the result. Well, those two separate flips of the same coin, those are independent events. You know, the result of the first coin flip has absolutely no influence on the result of the second coin flip. Both of them are 50% chance of landing heads and 50% chance of landing tails. So we just apply the restricted sort of conjunction here. What are the chances of the first flip landing heads and the second one landing heads? Well, we definitely multiply these together. And just, you know, as an aside, it certainly wouldn't make sense to add these together, right? If we added them together, we'd get 100%. And that's ridiculous, right? It's definitely not 100% chance that we're going to get 2 heads in a row here. So that just sort of makes it extra clear that what we're supposed to do is multiply these probabilities together. And that's just what we do down here. It's an and, so we multiply. 0.5 times 0.5 is 0.25, right? So 1/4, 25% chance, however you want to say it. So the chances of getting 2 heads in a row is obviously a lot less than the chances of getting just 1 head. And when I look at this kind of thing, I'm reminded of this really fun movie. Maybe some of you have seen it. It's actually based on a Shakespeare play, Hamlet. 2 characters in Hamlet are Rosencrantz and Guildenstern, and this movie just sort of focuses on their lives and sort of their adventures that's sort of paralleling the Shakespearean play. And there's a lot of banter, there's a lot of interesting conversations that Rosencrantz and Guildenstern have. And there's this running gag where one of the characters is flipping a coin over and over and over again. And it certainly appears as though this is a fair coin. You know, it really does have a heads and a tails side. There's nothing tricky about it. But every single time that he flips this coin, it lands heads. Every single time. Now, for any individual coin flip, that's not too surprising, right? It's just a 50% chance, but it keeps landing heads over and over again. Then it gets to the point where he gets heads 78 times in a row. So what are the chances of flipping a fair coin and having it land heads 78 times in a row? Well, we just apply this rule, right? We multiply the probabilities together. So 0.5 for every individual coin flip, 0.5 probability of it landing heads, and then we multiply it for every single coin flip. So 0.5 times 0.5 times 0.5 times 0.5, 78 times. In other words, that's 0.5 raised to the 78th power, and that gives us this insanely small number, right? So extremely unlikely that you could get 78 heads in a row. Not impossible, but really unlikely. Okay, moving on. Here's another thing that's going to become particularly important when we get to Bayesianism, which in this presentation we won't talk about Bayesianism at all. But it's called the negation rule. It's very simple. What's the probability of something not happening? Well, that's just 1 minus the probability of it happening. So when we're talking about rolling die, the probability of not rolling a 5, well, that's just 1 minus the probability of rolling a 5. So that's 1 minus 1/6, which is 5/6. If we're talking about playing cards, a deck of playing cards where all the cards are there and it's been properly shuffled, so it's very randomized. So before you look at any of the cards and you just draw one, every single card in the deck has an equal chance, as far as you know, of being the one that you draw. Well, so what's the probability of not drawing a queen? Well, what's the probability of drawing a queen? Well, we know that there's 4 queens in a deck, and we know that a standard deck has 52 cards. So it stands to reason that it's 4 out of 52 is the chance of drawing a queen. So what's the probability of not drawing a queen? 1 minus for 50 seconds, right? 1 minus 4 divided by 52. So that's 48 out of 52, and that reduces down to 12 out of 13. So pretty good chance that if you just randomly draw a card from a deck, pretty good chance it's not going to be a queen. Okay, so now things get a little bit more complicated, because before we were talking about mutually exclusive events or independent events, and now we need to start talking about things that are either not mutually exclusive or not independent. So first off, not mutually exclusive events. So this we have, say like we have a disjunction here, right? What's the probability of this happening or that happening? But there's also the possibility in the jointly exhaustive list, there's a possibility that both of these things come true. So a simple example, they do one that's very much like this in the book. What's the probability, from a standard deck of playing cards, what's the probability of drawing a queen or drawing a spade? Well, there's one event that actually, one result where both of these disjuncts is true when you draw the queen of spades, right? Because then you've drawn a queen and you've drawn a spade. So if you're calculating the probability of drawing a queen or drawing a spade, you need to make sure, well, the queen of spades belongs in both of these categories, right? It belongs in the category of queens and it belongs in the category of spades. So you need to be careful that you're not calculating in the probability of the queen of spades twice, because that's cheating, right, for calculating the probability. So here's what we do. What's the probability of these two things happening together? A or B? Well, it's the probability of A plus the probability of B, just like we had before with the restricted disjunction rule. But then you have to subtract out the probability of the conjoined event, right? Where both of the things come true. So this is like subtracting out one of the queen of spades probabilities. This gives us what's called the general disjunction rule. It's a disjunction still because it's or, and it's general because it applies to any situation, right? Whether the two things are mutually exclusive or not. And we can substitute in our symbols for the logical operators that we saw in chapter 7 on the truth table stuff, lowercase v here for the or, and then just this little dot for the conjunction for and. Okay, so let's look at an example. So the queen of spades example, what's just before we sort of do any actual drawing of cards just ahead of time, what do we think is the probability of drawing a queen? Well, we know there's 4 queens and there's 52 cards, so it's 4 out of 52. What's the probability of drawing a spade? Well, we know that there's 13 cards for each suit. There's 13 spades, 13 hearts, 13 diamonds, 13 clubs, and there's 52 cards total, so it's 13 out of 52. Also, that reduces to 1/4. But what's the probability of drawing the queen of spades? Well, that's just a single card out of the whole deck of 52, so that's just 1 out of 52. All right, so let's plug those numbers into our general disjunction rule, which we sort of have it laid out here. We plug them all in, and we get this number. Right? 4/13 is sort of the final probability that we get for drawing either a queen or a spade. All right, next up. Remember we had talked about this principle of indifference, right? It says, unless you're given reasons to believe otherwise, assume each possibility has an equal probability. But what about when you're given reasons for thinking otherwise? So other information could alter our assessment of the probability. So this is what's the situation when we have dependent statements or dependent events rather than independent. So the truth of one thing, let's call it P, affects the probability of something else, let's call it Q. So maybe that's a little bit confusing. So let's look at some examples here. So let's say that I've got a deck of cards and they're very well shuffled, so they're all randomized, and I draw one card and I look at it, but I don't tell you what the card is. And I ask you this, right? What's the probability that I just drew a diamond from the deck? Well, you know that diamonds make up 1/4 of the deck, so you'd say 0.25 or 25% or 1/4, however you want to express it. That's fine. But now let's say that I'm looking at my card and I say, so what's the probability I just drew a diamond given that the card I just drew is a red card? Well, that excludes all the clubs and all the spades because those are the black cards, and all we're left with are hearts and diamonds. And we know that there's an equal number of hearts and diamonds in a deck, so now you should probably guess that we've got about a 50% chance, right? A 0.5 probability that the card I drew is in fact a diamond, given that the card I drew is a red card. So that's kind of easy, and we'll actually go through the equations there, go through the mathematics to sort of show how that works. But just another sort of example that maybe is a little bit more real life. What's the probability that it will rain? Well, you know, so if that's all the information that I'm given, then I just have to think about, okay, for this region, how often does it rain? You know, we've got 356 days in the year. And so how many days out of the year does it actually rain? And so then I can do a quick calculation there. But what if I'm given more information? I'm actually told that the day we're talking about is a completely cloudless sunny day. All right, well, that adjusts my assessment of the probability that it'll rain today pretty dramatically, right? It's extremely unlikely that it's going to rain on a day that's cloudless and sunny. So yeah, I update my assessment of the probabilities based on this new information. Okay, so how is that symbolized? It looks like this. If we're talking about what's the probability of Q, whatever Q is, given some piece of information, P, it's like this. So what's the probability of Q given P? Or the probability of Q conditional on the truth of P, or conditional that P has occurred, or something like that. So these are now not independent things anymore, and so we can't just apply you know, something like the simple, you know, restricted conjunction rule or anything like that. So here's how we do it. What's the probability of Q given P? Well, it's the probability of both things happening together divided by the probability of P on its own. And we can't just use the restricted conjunction rule to calculate the numerator here, because these are not independent events. They're not mutually exclusive. So let's look at the red diamond example. So if I draw a card, what's the probability of that card being a diamond given that it's a red card? Well, intuitively, like we talked about before, you know, if I tell you, okay, I've got a red card here, what's the probability that it's a diamond? Well, you know that half the red cards are diamonds. So hopefully, when we run through the equation, the result that we get will be 0.5 or 1/2 or 50%, however you want to express it. So let's take a look. What's the probability ahead of time, before any of this happens, before any cards are drawn? What's the probability of getting a red card? Well, we know that half the cards in a given deck are red, so that's 1/2. What's the probability of getting a red card that is also a diamond? Well, all the diamonds are red, so this is really just the same as getting what's the chances, what's the probability of drawing a diamond from any given deck? Well, we know that 1/4 of the cards in a regular deck are diamonds, so it's 1/4, right? Or 0.25 or 25%, or however you want to express it. So we plug those numbers into the equation here, and it gives us, luckily, the intuitive answer of 1/2. So the calculation matches what we intuitively thought it would be. Okay, so I mentioned that you can't just use the conditional rule here to figure out what the probability of P and Q are here. I'm sorry, you can't use just the simple conjunction rule here. And so with this situation, we know so much about decks of cards. We understand how many of the different suits there are and everything, and how many of the different colored cards there are. So we just had a quick and easy intuitive way of giving us the answer here, right? The probability of P and Q is 1/4. But what if we don't have that, right? What if we need to sort of calculate that answer? Well, we can rearrange this conditional rule to get what's called the general conjunction rule. And so it ends up looking like this. What is, if we needed to calculate the probability of P and Q, Well, that's this. It's the probability of P multiplied by the probability of Q given P. So let's see how that would work out in our red diamond case. Hopefully it's going to come out to a quarter, and it does. We know what these values are to plug into the general conjunction rule equation here. P, the probability of P, the probability of drawing a red card, we already know that that's 1/2. What's the probability of getting Q, that is getting a diamond, given that it's a red card? Well, we already calculated that up here, right? It was 1/2. So we plug that into our equation. And so we get 1/2 times 1/2, which is 1/4. And that was our intuitive guess from the beginning for this situation. So that's good that the equation matched our intuitive guess. Okay, so that covers some of the real basics of probability, how to manipulate them, how to go about calculating probabilities. And so I'll go ahead and stop there.